Hello everyone, my name is Georg, and in this short video I would like to talk to you about parts of my master thesis with the title Aspects of Non-Abelian Gauge Theories with Fundamentally Charged Fermions. Now of course, this title seems quite generic, so for the sake of this video I would like to discuss some parts of my thesis in the context of quantum chromodynamics, the theory which describes quarks and gluons. Now before we discuss this theory in more detail, let's shortly take a look at the standard model. The standard model at the current point is the best theory we can come up with that describes our universe in terms of elementary particles. If we now restrict ourselves only to include quarks and gluons, we're basically talking about the strong interactions. And one of the key questions I had for my master thesis is, how do quarks and gluons interact? Now, to tackle this question, we have to first of all write down a theory, and this theory is quantum chromodynamics, or short QCD. It is the theory of strong interactions, and it explains how quarks and gluons interact with each other and eventually form mesons and baryons, such as the proton or the neutron. As particle physicists, we always start out by writing down some equations which describe our theory, and the information we want to get out is basically encoded in so-called propagators and vertices. These quantities tell us how the particles behave at different energies and especially how they interact with each other. At this point, I would like to highlight two key properties of QCD, namely color confinement and chiral symmetry breaking. Color confinement tells us that we can never observe quarks and gluons directly in an experiment. However, from a theory standpoint, these elementary particles are good tools to describe the strong interactions. The second property is extremely important for the subject of this video, because chiral symmetry breaking leads to the dynamical generation of constituent quark masses, which we will see later explicitly when I show you my results. Now, before I can do this, of course we have to answer the question, which method can we use to investigate certain properties of the theory? Now, first of all, QCD has a large coupling constant at lower energies. This basically means that the coupling strength between quarks and gluons increases towards lower energy scales. This restricts us of using strictly non-perturbative methods to investigate certain phenomena. The probably most famous non-perturbative method is lattice QCD, where the basic idea is that you simulate your theory on a discretized spacetime lattice. The problem with this is that this is very expensive to solve on a computer. So for my master thesis, I chose a different approach. Namely, I worked with functional methods, where the idea is that you do not discretize spacetime, but you set up equations which can then be solved to obtain information about the propagators and vertices of the theory. So finally, we are able to discuss the results of my master thesis. And during my calculations, a particular emphasis was placed on finding a solution to the so-called quark-gluon vertex. Now, the quark-gluon vertex is the lowest order correlation function that describes the non-perturbative interaction between gluons and quarks. Now, this quantity is actually kind of hard to calculate, but once you have found a solution, you see that there are different types of contributions to this vertex. The only important point here is that each line in this plot represents a different non-perturbative interaction between the gluon and the quarks. However, we can do a bit better. We can also solve for the quark propagator and the quark mass function. And the quark mass function basically tells you how the mass of a quark behaves at different energy scales. And if you look at the green curve here, we see exactly this dynamical mass generation I described before. We go from very small quark masses at very high energies to larger constituent masses at lower energies. And putting now everything together, we can basically conclude that dynamical chiral symmetry breaking is a phenomenon which is driven by the non-perturbative interactions between quarks and gluons. And with this, I would like to thank you for your attention.